We are going to start with lecture 3 of the chapter Introduction to Sets. So in our previous lecture we have talked about the set of integers, the set of prime numbers. We have proved that the set of prime numbers, it is an infinite set. Then we have talked about the set of real numbers. It consists of rational and irrational numbers. We have seen some examples over there. And finally we have solved some linear inequalities in one variables. Now in this next lecture we will talk about subsets and supersets, and then we will look into the definition of universal set and the power set. So we start this with understanding of some quantifiers. The first one that we will use in our lectures, that is for all quantifier. For all quantifier means, suppose we have the statement for all x in the set of integers z, x plus 0 is equal to x. It means we are saying that if we have the set of integers, then for every integer z, we are saying for all x in z means for every integer z, x plus 0 is x. How we can write this? For all x, this term, for all we are saying this is a quantifier which quantifies that for every element of this set z. We write it like this. We are saying for all, this is the symbol for all we have. We are saying x. How we read this? We are saying it is for all x in the set of integers. Where these x they are lying, they are belonging to the set of integers. What property holds over here? We are saying x plus 0 is equal to x. It means if you consider any integer you will consider, you will have x plus 0 is equal to x. This is called for all quantifier. It is represented in this form. The next quantifier that we have, it is the there exist, or we are saying existential quantifier. Now suppose we are talking about there exists an integer x such that x square is equal to 4. If I am talking about x square is equal to 4, we have x is equal to plus minus 2. This thing holds only for two integers over here. It is not holding for all integers. So we are saying that there exist, in this case, two integers such that x square is equal to 4. There is solution for this statement. There are two integers. How we write this statement? We are talking about there exists. How we represent there exists? We represent it in this form. This is the notation for there exists. We are saying an integer, there exists x. X is an integer. And what it satisfies? It satisfies x square is equal to 4. Now compare these two things. Now if we compare these two things, it should be clear to you when we are saying for all x belongs to z, it means this statement x plus 0 is equal to x, it holds for every integer. X square is equal to 4. There exists an integer. At least one integer is there for which this thing holds. If we are saying there exists an integer for which x square is equal to 4, we are not talking about all the integers. So this is the second quantifier that we need right now. It is the existential quantifier. This how we read it. We are reading there exists x in z, that is x is an integer such that x square is equal to 4, and this is for all x that are integers, x plus 0 is equal to x. This is how we read these terms. Next is this symbol we are talking about. This symbol we are using. This is the implies symbol. Implies means if we are talking about if a number is n is divisible by 6. I am talking about this statement. Then if a number is divisible by 6, then we are saying that n is divisible by 2 and 3. What this thing means, we are talking about a statement that a number n is divisible by 6. Then what will happen? N is divisible by 2 and 3. How we can write this? We are saying 6 divides n. We have a number. If a number n is there, and we are saying 6 divides n, this then we are having over here, this then. We are saying this thing implies us if 6 divides n, this thing implies us that 2 divides n and 3 divides n. This is how we can use this symbol implies. Implies means one statement, it implies the second statement, or we are saying over here that one statement, it indicates or leads to the condition of some other statement. So these are the 3 symbols or notations that you should now keep in your mind. These will be used in our next slides. So let us consider another example. We are having the set A, it has elements 2, 3, 5, and we are having the set B, it has element 2, 3, 5, 7 and 9. I am talking about 2 statements. One statement I am saying, for all x in A, we are saying we have x belongs to B. I'm talking about for all x in A, we have x belongs to B. We have to check whether this statement is true or false. I am saying for all x belongs to B, we have x belongs to A. I am talking about these 2 statements. When I am talking about this first statement, for all x belongs to A, we have x belongs to B, I have to check this. It means I have to check for every element of A. The first element of A, it is 2. We are saying 2 belongs to A. This implies 2 belongs to B. 3 belongs to A implies 3 belongs to B. 5 belongs to A, this implies 5 belongs to B. For every element of A, we have that element belongs to B. It means this statement, this is true. This is the meaning of this for all. If I am talking about for all x belongs to B, x belongs to A, I am talking about this implies, I am talking about whether this statement is true or false. Now consider the element 7. We are saying for all. For 2, 2 belongs to B, 2 belongs to A. 3 belongs to B, 3 belongs to A. 5 belongs to B, 5 belongs to A. But now if we consider 7 belongs to B, but 7 does not belong to A. 7 is an element in the set B which does not belong to the set A. It means that we cannot say that for all x belongs to B, x belongs to A, because there exists, we are saying there exists x belongs to B such that x does not belong to A. We are having at least one element which belongs to B, but it is not the element of A. So this is the meaning of these terms. We are saying this is for all and this is there exists. Another thing that we get from this example, that if I try to represent these 2 sets using the circles, I am talking about this is the set B and this is the set A. How I can represent, why I am drawing this circle inside it? Look over here. We are saying A has elements 2, 3, 5. A has elements 2, 3 and 5. B has elements 2, 3, 5. 2, 3, 5, they are inside B, and further it has elements 7 and 9. Further it has elements 7 and 9. So from this, what we are saying, for all x belongs to A, x belongs to B. If the element is in A, then it is in B. So this leads us to the definition of a subset. This is the definition of a subset. So we are saying a set A is a subset of B if every element of A is an element of B. Every element of A means for all x belongs to A, We are talking about every element of A. We have X belongs to B. If this statement holds for two sets, then we will say that A is a subset of B. This is the notation for subset. This is the notation for subset. So if we look at this example over here, we are saying this set A is a subset of B because every element of A is an element of B. Or we can say, this is the term subset we have, or we can say B is a superset of, this is the notation for superset. You can use any of these two. Either you will say it is a subset, A is a subset of B, or you will say B is a superset of A. Meaning is that for all elements X belongs to A, X belongs to B. Another important thing that we have over here, that I'm using this symbol over here. I'm using this symbol over here. Suppose I am talking about two numbers. We are saying 2 is less than equal to 3. Is this statement correct? And I am saying 2 is less than 3. Then I am saying 2 is less than equal to 2. And I am saying 2 is less than 2. Observe these statements very carefully. We are saying 2 is less than equal to 3. This statement is correct. We are saying it is less than or it should be equal to. 2 is less than 3. This is correct. 2 is less than equal to 2. Now equality holds over here. This statement is correct. When we are saying 2 is less than 2, this statement is false because 2 is not less than 2. Similarly, what this thing means, if two sets they are equal, then what will happen? Every element of A is an element of B because both the sets they are equal. So we will say A is a subset of B. If two sets they are equal, we can write A is a subset of B. Now we are talking about that we have two sets A and B. So these are the two sets we are talking about, A and B. What happens over here? That A is a subset of B, but we have A is not equal to B. I am talking about the case 2 is less than equal to 3. What happens in this case? We are saying 2 is not equal to 3. We are talking about this case. I am again explaining. We have A is a subset of B. A is a subset of B, but A is not equal to B. If both these conditions hold for two sets, we just write it like A is a, this, how we read this? This symbol we are putting over here, this is like this. So we will say this is proper subset. This is symbol for proper subset. This symbol we are reading as subset. Subset means it is a subset or equal to, proper subset or equal to. When we are saying proper subset, when it is written A is a proper subset of B, it means that every element of A is an element of B, but A and B they are not equal sets. This is what we mean by proper subset. So next we have certain results over here that we will discuss now. The first result we have is every set is a subset of itself. So we are saying, suppose we have a set A. Let A be a set. We have to prove that A is a subset of A. Now what is the definition of subset? We are saying A is a subset of B if for all X belongs to A, we have X belongs to B. In this definition, if we put A is equal to B, so what we need to show in this definition, if we put A is equal to B, what this will become, it is for all x belongs to A, we have to show that x belongs to A. And this statement, it is always true because every element of A, by the definition of the set, it is element of itself. This statement is always true. So we are saying that A is always a subset of A. We are not talking about proper subset over here. Keep this in mind. This symbol we are using over here, this is for subset, not the proper subset. So we are saying every set is a subset of itself. Next is the empty set is a subset of every set. Next thing we have is the empty set, it is a subset of every set. So empty set we are talking about phi, and we are proving that we have a set B, then phi is a subset of B. This statement, to prove this statement, what we have to prove, for all x belongs to phi, x belongs to B. If I am talking about x belongs to phi, is there any element? There is no such x which belongs to phi. It means there is nothing to check over here. There is no element over here, means there is nothing to check over here. We are saying that it has no element. So by default we are saying that phi is a subset of every set. Or when we were talking about the subset, when we were talking about the two sets A, say it has elements 1 and 2. We are talking about another set B, it has elements 1, 2, 3. I ask you whether B is a subset of A or not. I ask you whether B is a subset of A or not. What you try to do is, you try to find an element in B which is not an element of A. These are called the counter examples. So we are saying, if I have to prove A is a subset of B, I take an element 1 over here, it exists over here, B is there, B is present, this element 2 is present in B. If in place of this I am talking about the set phi, it has no element over here. So we are saying that there is no element of x which is not present in B. There is no element in x which is not present in B. So that is why we are saying that phi is a subset of B. These two proofs that we are talking over here, they are quite abstract. These are not that simple to understand at this moment. But as we will move further, things will become more clear to you and the idea of these proofs will be more clear to you. So right now you can just look at these results that every set is a subset of itself. Keep this in mind. Second, we are saying that the empty set is a subset of every set. So just keep these two results in mind right now. Next we are talking about proving equality of sets. If suppose two sets A and B they are given to us and we want to prove that those two sets they are equal, what we have to do? We are going to prove that A is a subset of B. This is method how we will prove that two sets they are equal. We have to prove that A is a subset of B and B is a subset of A. This is the standard method we will have. Let us understand this with an example. Suppose I am talking about the set A. It is x such that x square is equal to 4 and set B is there. We are saying this is equal to -2 and 2. These are the two elements that we have. We have to show that these two sets they are equal. We are going to check whether these two sets they are equal or not. So in the first step, we are going to check whether A is a subset of B or not. So A is a subset of B if we want to prove. What we are going to do? We are going to take x belongs to A. We are going to consider an element from this set A. So the elements of this set we are saying one element is there, that is minus 2, and that element it belongs to B. Another element we have, it is 2, it belongs to B. So what we obtain is that for all x belongs to A, x belongs to B. So from this result we conclude that A is a subset of B. Second part. Now we are going to prove that B is a subset of A. We are going to prove that B is a subset of A. Consider an element minus 2 from B. Minus 2 satisfies this condition. Minus 2 square is equal to 4. So this implies us minus 2 belongs to A. Consider the second element from B. We are saying 2 belongs to B. 2 square belongs equal to 4. This implies us 2 belongs to A. What we obtain is for all x belongs to B, we have x belongs to A. For every element of B, we have that belongs to A. So combining both these, from this what we obtain is B is a subset of A. We have shown A is a subset of B. We have shown B is a subset of A. Combining these two results, we obtain that A is equal to B. Combining these two results, we get the desired result. So this is how we can prove, if any two sets are given to you, this is how you can prove that the two sets, they are equal. So we have to show that A is a subset of B and B is a subset of A. Then combining both these results, you will get that both the sets, they are equal. Next we have is set of sets. So we are saying a set of set means a set whose elements themselves, they are the set. So if we consider a set A, now the elements, look at this set over here. Suppose I am writing 1, 2. So these are the two numbers. If I am putting them in the curly bracket, this is a set. So what this thing looks like? We are saying we are having a set A. It contains the set 1, 2. It contains a set which contains the element 1, 2. Another set which contains the elements 3, 4, and another set which is 5. So to get a better understanding of this thing, let us consider the circle diagrams we were talking about. Suppose this is the set A I am talking about. This is the set A. This is the set 1 having the element 1, 2. This is the set having the elements 3, 4, and this is the set having the element 5. And there is another set having the elements 1, 2, 3 and 4. There is a set that has elements 1, 2, 3 and 4. It looks like this. This is set with elements 1, 2, 3 and 4, numbers 1, 2, 3 and 4. Over here what we can see, A has the set 1, 2 in it. Set, this is set. A has a set which has elements 1 and 2 in it. A has a set which has elements 3, 4 in it, and A has a set which has no element in it. Now things are going to become a bit complex now. If I am talking about, this is the set B, say this is the set B, it has the elements 1, 2, 3, 4. If I ask, does 1 belongs to B? Does the number 1 belongs to B? So when I am saying belongs to, it means that that number should be present in B. This number 1, it is present in the set B. Now if I ask, does 1 belongs to A? In the set A, we have 3 sets. We have no element 1 over here. So we are saying 1 does not belong to A. What belongs to A is this complete set. So what we are going to say, 1, 2, it belongs to A. What kind of elements A has? A has sets in it. The elements that the set A has, we will write first element 1, 2, and we are saying this element 1, 2, this complete set belongs to A. We are not saying 1 belongs to A, we are not saying 2 belongs to A, we are saying that this set 1, 2, it belongs to A. So let us try to understand this set of sets, that what this belongs to means over here, and some other notations with some examples. We have to tell whether the following statements they are true or false. First statement, A belongs to the set having the elements A, B and C. We are saying A belongs to A, B and C. If we draw the circle diagram, we are having A, B and C. So A is clearly present over here. So we are saying that this statement it is true. Now consider this set. This set has a set containing the element A. Over here it is A over here. Over here it is the set containing the element A. Then we have it is B, and then we have it is C. These are the 3 elements of this set. So does the set A belongs to this set? Yes. This element is present over here. So we are saying that this statement it is true. This is the element of the set. We are talking about thus this thing is present in this set. Yes, this thing is present in this set. Over here we are asking, does this thing is present in this set? Yes, this thing is present in this. Consider the next case. Does this belongs to this? We are talking about the set has elements A, B, C. Look at this. Is there anything which looks like this? No. This is the element A that we have. We have no element like the set having the element A over here. So we are saying that this statement it is false. This set does not contain an element which itself is the set containing the element A. Next, look at this. Now we are talking about the subset conditions. The previous case we were talking about the belongs to. Now we are talking about the subset. Let us again talk about the definition of the subset. When we start the definition of the subset, we are saying A and B are 2 sets. First thing is A and B are 2 sets. If for all x belongs to A, x belongs to B, then A is a subset of B. So for a set A to be a subset of B, first thing is it should be a set. Both of them should be a set. This set A is the set having the element A. First of all, it is a set. B is the set having the elements, the set containing A and an element B. Is A a subset of B? You have to check that condition. we are saying consider the element A over here. We are saying A belongs to A. This thing is clear to you? A belongs to A. Does A belong to B? Is there an element A over here? Again, look at this condition. It has elements like this. A does not belong to B. It is the set A which belongs to B. There is no element A in this set. So we are saying that A does not belong to B. So this statement, it is false. A is not a subset of B because this set has an element A which is not present in the set B. But if we are writing, I'm talking about this, the set A, it belongs to the set A, B. But set A, it is not a subset of set A, B. I am again explaining these two things. When we are saying belongs to, this element is as it is present over here. This element, I am not talking about the set. Whatever, it is a set, it is an element, whatever we have, it is exactly present over here. When we are talking about subsets, first condition is there should be a set. Consider the element of that set. That element should be present over here. It is not present at this point, so this is not a subset. Second, this set is a subset of A, B, C. Now, again, we are considering A is equal to set A, B is equal to set A, B, C. We want to check whether A is a subset of B or not. So the condition again we have is for all x belongs to A, the element, first element we consider over here, it is A belongs to A, and we have corresponding to it A belongs to B. It means every element of the set A, it belongs to the set B. There is only one element, it means every element belongs over here. So this thing implies us that A is a subset of B. So this thing is true. The statement is true. Next, A is a subset of A, B, C. Look at this element over here. This is the element A. When we are talking about the definition of subsets, we are saying A and B are two sets. Is this a set? No. This is an element, not a set. So we cannot talk about subsets over here. So this statement we are saying this is false. We cannot talk about subsets because we cannot consider an element from this set. First of all, it should be set, only then this definition it is applicable. So we cannot talk about subset over here. So we cannot say that A is a subset of A, B, C. Now let us consider another example. This set A is given to us. This set A is given, and if some statements are given, we have to tell whether those statements they are correct or not. So this set A, this is the set A I am talking about. It has elements of 1. Then it has a set having the element 2. Then it has a set having the elements 3 and 4. And then it has an element 5. 1, set having 2, set having 3, 4, 5. There is no element 3 in this set. It is a set. It is like a bag inside a bag. It is a bag inside a bag. Number of elements in A is 4. How many elements are there? 1 element, 2 element, 3 element, and 4 element. So this statement it is true. Next is 2 belongs to A. Is there an element 2 over here? No. there is a set having element 2 in it, there is no element 2. Elements we have 1, a set, and 5. If suppose in place of this I am writing we have B is equal to 2 and C is equal to 3, 4, how this set will look like? This is A, 1, B, C and 5. These are the elements of this set. Is there any element 2 over here? No. So this statement it is false. Set 2 is a subset of A. We are saying set 2 is a subset of A. Now if I am talking about set 2, suppose I am saying this is the set D we have. So to prove that D is a subset of A, we have to prove that for all x belongs to D, x belongs to A. X belongs to D means I am talking about an element 2 belongs to D, but 2 does not belong to A. There is no element 2 over here. So this statement it is false. Consider another statement. I just changed this statement. Suppose I am talking about, in place of this I am saying, is this a subset of A? Is this a subset of A? Suppose we are writing this is D. So what we have to do, we have to check if x belongs to D, then x belongs to A or not. X belongs to D. What is the element in this set D? The element in this set D, it is the set having the element 2 and that belongs to D. And this element 2, we are writing this is basically B. So we are saying 2 also belongs to A. It means for every element of this set D, it is present in the set A. So this statement it is true. Observe these things very carefully. 2 is a subset of A. Set having element 2 is a subset of A is false. Set having a set containing element 2 is a subset of A is true. Next, 1, 2. We are saying 1, 2. Is this a subset of A? To check this, consider the two elements over here. It has one element 1 and another element 2. Suppose I am saying this set it is D. So we are saying 1 belongs to D and 1 belongs to A. 2 belongs to D, but 2 does not belong to A. There is no element 2 in the set. It means that not for every element of D it belongs to A. So this statement it is false. It is not a subset over here. Next is the set 3, 4 is a subset of A. So consider the element 3 belonging to the set 3, 4, but 3 does not belong to A. There is no element 3 over here. It means this is not a subset. 1, 2, 3, 4 is a subset of A. False. 1 is present in A, 2 is not present in A, 3 is not present in A, 4 is not present in A. So this statement is false. Next is understanding the empty set and sets containing the empty set. So under empty set we know the set having no elements, either we represent it like this or we represent with phi, and if we use the circle we are using the empty circle over here. Now we are talking about a set containing the empty set. Suppose we have a set A. First thing about empty set we have already studied. It is for any set phi. Phi is a subset of A. This thing we have already studied. That phi is always a subset of A. I am talking about subset. I am not talking about element of. Phi is a subset of A. I am not saying phi belongs to A. This is the case I am going to talk now. Phi belongs to A. I am having a set A. Its only element is phi. Now try to understand this situation. One set I am writing this. This is the empty set. It has no element. One set I am saying it is a set having the empty set in it. This is a presentation of empty set. We are saying we have a set A. It has an element in each which is empty. How many elements are there in this set A? It has one element. This set has one element. So number of elements in A is equal to 1. Now moving further, a set containing phi and A. Now we are talking about the set. We have started with the set phi. We have defined a set A. A contains the element phi. Now we are talking about another set and it has the elements phi and A. Suppose this is the set B we are talking about. It has the elements phi and A, or we can write it has the elements phi set that is empty. For empty set phi, how many elements are there? Number of elements in phi that is equal to 0. For the set A, it contains the empty set. We are saying this is the set A. Number of elements in A that is equal to 1. Move on to the set B. This is the set B we are talking about. It has the empty set. Another set having the empty set. Number of elements in B that is equal to, how many elements are there in B? This is one element, this is another element, this is the element phi and this is the element A. Number of elements in B that is equal to 2. Next, consider another set and that set contains phi A and B. Now this set, it contains phi A and B. So what will happen over here? Suppose this is the set C. It contains phi A and B. It contains phi. What is A? It is the set containing the empty set. What is the set B? It is a set which contains the empty set and another set containing the empty set. How we are going to represent? How many elements are there? This is one element, this is second element, this is the third element. If I have to represent this set C, I am saying it has the empty set in it. It has a set containing the empty set in it. It has a set having the empty set in it. This is the set phi. This is the set A. Then it contains another set. It contains another set which contains the empty set. It contains a set having the empty set. So this is the set C that we have. How many elements are there in this set C? One element, two element, three element. All this set, it contains a set having empty set. So basically we are talking about a bag having balls. Balls are just like the elements, empty bag is like the empty set. We are saying this is a bag it contains another bag which is empty. It contains a bag which contains another bag which is empty, and continue it like this. So this is how we can represent these sets. These are the sets having the these are the sets containing the empty sets. So what we obtain from this is the empty set has no element. The set containing phi, it is not an empty set as it contains one element. And what we can see over here, that set can contains other sets as elements, and this leads to the nested structures with increasing cardinalities. And the distinction between the empty set and set containing empty set, we have seen over here that the empty set has no element, whereas this set containing the empty set, it has an element in it. It has a set that itself it is empty. Now next we have an illustration over here. It is, we have to check whether the following statements are true or false. So first is phi belongs to the set A, B, C. So when we are saying phi belongs to the set, phi is this set we are talking about, this is the empty set. So look at this set. It has how many elements this set has? It has elements A, B and C. Is there any set over here which is empty set? So we are saying that this statement it is false. There is no set in this set which is empty. But if we are talking about this condition that phi is a subset of ABC, we have seen that empty set is a subset of every set. So this statement is true. So we are saying that phi, it does not belong to the set ABC, but phi it is a subset of the set ABC. Look at this condition. We are saying phi belongs to phi ABC. How many elements this set has? It has A, B, C, 3 elements. Then it also contains a set which is empty. So we are saying phi belongs to this set A, B, C. So this statement it is true. If we are talking about the set phi, this element we are saying it is a subset of ABC. What we observe over here? Consider this element. We are saying phi, it belongs to the set containing phi, but phi does not belong to the set containing elements A, B, C. So for an element phi which belongs to this set, that element does not belong to the set ABC. It means that this set is not a subset of this. So this statement we have it is false. This statement is false. Next we have is the definition of the universal set. So we are saying if there are some sets under consideration, then there exists a set which is superset of each one of those sets, and that is set is called the universal set. So let us look at some examples over here. Suppose I am talking about three sets A, B, C are there. A, B, C. These are three sets we are talking about. Universal set we are saying we want to find a set that is superset of all these three sets. If suppose I am talking about the set, we represent universal set with U. I am talking about the set which contains elements 1, 2, 3, which contains elements 2, 3, 5. Repetition is not required. 2, 3, 4 and 5. Then 6 and 7. What we observe over here that U is the superset of A, U is the superset of B, U is the superset of set C. So we can consider this set as the universal set. This is not only the universal set. If I am talking about the set of natural numbers, it is also a superset for all these. if I am talking about the set of integers, if I am talking about the set of real numbers, so all these are supersets of the set ABC. So you can write U as this is the universal set for these three sets: natural numbers, integers, rational. You can write the answer in any form. So we are saying that any of these sets, these can be the universal set for these particular sets. So when we are dealing with numbers, so the universal set may be the set of natural number, it may be the set of real numbers, it may be the set of integers. So depending upon the situation, we can consider different universal sets. If we are talking about some set of letters, then suppose I am talking about a set having elements A, B, another set having elements C and F. These are the two sets given to us, and we want to find the universal set corresponding to these two. So we can consider the set of all letters of English alphabet as the universal set. So we are saying we can consider U is equal to A, B, C, so on up to Z. This can be considered as the universal set for these two sets having elements A, B and C. So we are saying if we consider the set of letters in the English alphabet, then that set can be considered as the universal set for this particular case. Next we have is the Venn diagrams. We have seen the circle diagrams. Now the more formal way we have, that is the Venn diagrams. So we are saying in this context, the Venn diagram, it is usually represented with a rectangle with subsets depicted as the circles inside it. So let us try to understand what we mean to say by this. Let us consider an example. We are talking about the universal set U. It consists of all English letters, and we are talking about the sets A and B. Now what Venn diagram is? We are saying the universal set that we will have, we will represent it with the rectangle. We will draw a rectangle over here. We are saying this is set U. That is the universal set. You cannot change these things at your own. These are the standard notations now. We are saying universal set that we have, we will represent them with the rectangle. So it is the set containing all the sets under consideration. We are talking about two sets A and B. What we are going to do, we will draw this set A. This is the set A. It contains the elements A, E, I, O, U. You should not confuse these two things. You can, if you are confusing, remove this element over here. You will remove this element over here, then this set will become different. Otherwise, you can leave it like this. We are saying we have a set A, it has elements A, E, I, O and U. These are the alphabets that we have, that we are taking from the universal set. So we write it in this form. You must not confuse these kind of things. We have the set B. B has the elements C, D, G, H, L and M. So what we are trying to say over here is that universal set, it is represented with the rectangle. This rectangle, it is representing the universal set U whenever we are talking about the Venn diagrams. Then when we are talking about the sets, they are represented with the circle. Each subset of this set U, we are saying A and B, these are the two sets. U is a universal set, means both these sets are the subset of this U. So these subsets A and this subset B, they are represented with the circles. And if suppose I am talking about this case, if I am talking about the circles like this common region, this will represent the elements common between them. We will see these terms in our next slides. So right now, it is sufficient for you to know that this rectangle that we are drawing over here, this is representing the universal set, and these circles that we have drawn over here, they are representing the sets. Next definition we have, it is the power set. So a set that consists of all subsets of a set, it is called the power set. If any set is given to us, we write all subsets of that set, then the collection, then the set that is formed with those subsets, that is called the power set, and it is denoted by P of A. Corresponding to the set A, it is denoted by P of A. And if A has n elements, then P of A will have 2 raised to the power n elements. Proof we will see in our next slides. So right now you can look at these two results, that if A is a set, P of A, power set of A, it is the set of all subsets of A, and the number of elements in the power set of A, number of elements, we are saying cardinality of the power set of A, that is 2 raised to the power n, where n is the number of elements in the set A itself. So let us explain this with some examples. First is, consider a set that is having a single element. We are saying A is the set, it has single element 4. What are the possible subsets of A? We are saying number of elements in A, it is 1. There is only one element. So number of elements in power set of A, that will be 2 raised to the power 1, that is equal to 2. Now what are the 2 elements? We are talking about the power set of A. First of all, it is a set. Now what are the possible subsets over here? We know that phi is always a subset of a set. We are talking about all the subsets. Phi is a subset of a set. Another subset we have over here, we are talking about subset. Another subset we have over here, it is the set itself. It is this set having the element 4, it is the set itself. So we are saying this is the power set of the set A. It has 2 elements. One is the element phi and another is the set itself. Things will be more clear to you as we move towards our next examples. Set B is given. It has elements 2 and 3. So number of elements in B, that is equal to 2. So number of elements in power set of B, that will be 2 raised to the power 2, that is equal to 4. Now we have to write the power set of B. It is a set. We are talking about the set B. Phi is always a subset of the set. That set itself, it is always the subset of that set. These are the 2 sets that are always the subset of the given set. Now we have 2 elements, 2 and 3 over here. If I write a set having element 2 and if I write a set having element 3, are these 2 a subset of B? Yes, because for every element 2 over here, 2 is present in B. It means this set is a subset of B. If I am talking about this element 3, this set is a subset of B. We are saying the other 2 subsets we have over here, it is the set 2, that is the set 3. So these are the 4 possible subsets of the set B. Let's move on to our next example. Next is the empty set C we are talking about. How many elements this set has? Number of elements in C that we have, it is empty set, it has 0 elements. Number of elements in power set of C, that is 2 raised to the power 0, is equal to 1 element. There is only one subset over here. What is that subset? We are talking about power set of C. We know that phi is always a subset of every set. So phi is also a subset of the empty set. So we are saying power set of C, where C is the empty set. The power set of C, it has only one element, that is that set itself. So we are saying in number of elements in power set of C, it is 1. So when we are talking about the power set, we are talking about the set of sets. It is a set containing the sets. Next, consider a set D with 3 elements. We are talking about number of elements in D, that is equal to 3. So number of elements in power set of D, that is 2 raised to the power 3, that is equal to 8. There will be 8 elements. We are talking about power set of D. We are saying it is set of sets and it contains 8 elements. 2 elements we already know. Phi is always the subset. The set itself, it is always the subset of that set. These are the 2 sets we are talking about. Now what are the remaining 6 sets? What are the elements over A, B, C? If I write the set A, it is a subset of this set. If I write set B, it is subset of this set. If I write element C, set having element C, it is subset of this set. Now, if I write the set having elements A, B, it is subset of this set. If I write the set having elements A, C, it is the subset of this set. If I write the set having elements B, C, it is the subset of this set. So how we are writing? We are writing empty set is the subset of this set. Power set, when we are talking about, it is collection of sets. It is set of sets. Phi, we are talking about empty set. Then we are listing, we have considered only one element A, B, C, and we are talking about the set containing A, set containing B, and set containing C. They are the subsets. We have considered 2 elements A, B, A, C, and B, C. These are the possible combinations that can be made. These 3 are the subsets of this set. And finally, we are saying that set itself, it is a subset of that set. So these are the 8 elements that we have in the power set of the set D. Next, we are talking about the set E that has elements A and the set having the element B. We are defining B is equal to having the element B only. So what we can do over here? We can write the set E as A comma B, where B, it is itself a set. What we have to do? We have to write the power set of the set E. So we are now considering this set over here. So what is the power set or number of elements in E? First of all, number of elements in E is 2. Number of elements in power set of E is 2 raised to the power 2, it is 4. Power set of E, if we are talking about, it has elements phi, set having element A, set having element B, and set having elements A and B. It is set of sets having these elements. Now, what we are saying B itself, it is a set. So we are saying the power set of E, it is, this is A. Now look over here, it is set containing the set B. What is the value of B? It is the set B that we have. Next, A comma, what is the value of this set B? It is the set having the element B. We are talking about, this bracket is closed over here. So these are the 4 elements of the power set of E. So these are the 4 elements that we have. Next is, we are given the set A is equal to X such that X is equal to n square and value of n they are 1, 2 and 3. So what is this set? When we substitute n is equal to 1, X is equal to 1. When we substitute n is equal to 2, X is equal to 4. When we substitute n is equal to 3, X is equal to 3. This implies us X is equal to 3. So we are saying set A has elements 1, 4 and 9. Number of elements in A is 3. Number of elements in power set of A is 2 raised to the power 3 is equal to 8. Now what we have to do over here, we have to write the proper subsets. I am not talking about the power set. What we are talking over here is how many proper subsets are there. So if I have to write the power set of the set A, we are writing it is 5. Then the next we will have it is the element 1. Then next we will have the element 4. Next we will have the element 9. Next we will have the element 1 4, 1 9, 4 9, and the set A itself. These are all the subsets that we have. Out of these sets, when we are talking about the set 5, this is called the trivial subset of this set. This is called the trivial subset. So in general, when we are talking about the proper subsets, and this A, this we already know that this is also not the this is not the proper subset. I am talking about two different terms. Phi is called the trivial subset. What is the definition of proper subset? When I am saying proper subset, the definition was A is a subset of B, but A is not equal to B. If we are talking about this element A, it is satisfying this condition. So we are saying that is A is not a proper subset. This A is not a proper subset. So number of proper subsets of A that we have, that A is removed, number of proper subsets of A, that is given by 2 raised to the power n minus 1, that is 8 minus 1 is equal to 7, because this A, it is not a proper subset of this set A. Next example we have is the next question we have is, let S be the set. It has elements 1, 2, 3, so on up to 100. We have to find the number of non-empty subsets A of S such that the product of the elements in A it is even. So this is the set S given. So what are the possible subsets over here? We are writing the possible subset. One subset will be 5. We are writing the empty set. Next is the sets with the single elements 1, 2, 3, so on up to 100. Then next subsets will be 2 with the 2 elements 1, 2, 1, 3, 1, 4, so on up to 1, 100. Next if we list, we will have 2, 3. These 2 elements are there. Then 2, 4, 2, 5, so on up to, like this we will have 99, 100. Then we will have sets with subsets with 3 elements. We are talking about 1, 2, 3. Next 1, 2, 4, and continuing like this. How many? We are not saying there are infinite. There will be last. It will be this set S itself. This is also a subset of itself. So how many total subsets are there? We are saying total subsets that we have, that will be 2 raised to the power 100, because there are total 100 elements. Now we are talking about a non-empty subset A of S. We are talking about non-empty subset A of S such that the product of the elements in A is even. Now look at these terms. There is only one element, the product odd. So out of these, when we are talking about these elements, odd, the product will be even for this, product will be even for this. There is only one element, so that element itself will be there. Now suppose I am talking about this element 1, 2. What is the product? 1 into 2, that is equal to 2. It is even. 1 into 3 is 3, it is odd. 1 into 4, it is even. So we are talking about that. Suppose I am talking about this term. I am talking about 1, 2, 3. It is 2 into 3, 6. Product is even. So first of all, let us look at the case when the product will be odd. We are talking about when the product of elements is odd. So the product of the elements is odd if all the elements in that set, they are odd. It is odd if all elements of the set is odd. If there is at least one even number, then that product will be even. It means we are interested in calculating the number of subsets which have only the odd numbers. So out of these, we are saying there are 50 even numbers and 50 odd numbers. We have 1, 2, 3, 4, total 100 numbers are there. 50 are even and 50 are odd. We are interested in all subsets of these odd numbers. So how many subsets will be there that are only formed with the odd number? That will be 2 raised to the power 50. We are talking about the number of subsets that have only the odd elements. If we are talking about this 1, this 3, if I am talking about over here 1, 3, 1, 5, 1, 7, we are talking about these elements. So how many such subsets are there which consists of only odd elements? There are 2 raised to the power 50. And for these subsets, the product is odd. For all other, the product is even. Total number of subsets we have, it is 2 raised to the power 100. Number of subsets with odd product. Number of subsets with odd product, that is 2 raised to the power 50. So number of subsets with even product, number of subsets with even products, that is 2 raised to the power 100 minus 2 raised to the power 50. So how we can write this? If we take 2 raised to the power 50 common, we are left with 2 raised to the power 50 minus 1. So this is the answer for this. This is the number of subsets of S, that is the number of elements in A, and A consists of those subsets, the product of whose elements it is even. Next we have two finite sets having m and n elements. We have two finite sets. Say we have two sets. One is a set A, another set we have B. This has m element, it has n elements. The total number of subsets of the first is 2 raised to the power m, 2 raised to the power n is 56 more than the second set. So when we are talking about 56 more than the second one, we are talking about 2 raised to the power m minus 2 raised to the power n, that is equal to 56, and we want to find the possible values of m and n. So how we are going to calculate these values? We can write this 56 as 64 minus 8. You can write this is 2 raised to the power. The value we will have, it is 6 minus 2 raised to the power 3. It means that the possible values of m, they are 6, and for n it is 3. So we have to find the value of m and n. We are saying the m 6 and n 3. If we will substitute, then it will satisfy the condition of this problem. Next is constructing examples and counter examples. So some statements are given to us and we have to determine which of these are false. So first statement is, if A is a subset of B and X does not belong to B, then X does not belong to A. We want to check whether this statement it is true or false. So we try to construct some set over here which satisfies this condition, or we can say that we are trying to explain it with the Venn diagram. We are saying if A is a subset of B, this is the set B we have, and A is a subset of B, and X does not belong to B. This is the element X we have, it does not belong to B, it is element of the universal set which is not the element of B. Then X does not belong to A. So this thing is clear to us that this statement it is true. Now how we are going to write? One is this explanation we are giving, that we have drawn the Venn diagram and we can see over here that if X does not belong to B, then it cannot belong to A. So what we are going to do, we are going to use the definition of the subset which says that if X belongs to A, then X belongs to B. We are talking about, if we are talking about this element X which does not belong to A, we are saying let us consider an X which does not belong to B, and suppose we are saying X belongs to A. Then what will happen? Then because of the definition of the subset, this thing will become contradictory. It means what we are trying to say is, I am not giving any formal proof over here, I am just giving an explanation. It means that if A is a subset of B and X is not an element of B, then X cannot belong to A. Next, so the previous statement that we have, it is true. Next is, if A is a subset of phi, then A is equal to phi. A is a subset of phi means that for all X belongs to A, we have X belongs to phi. For every element X which belongs to A, it will belong to phi. If A is non-empty, then there exists some X in A, and by this definition we will have X belongs to phi. Again, look at this condition over here. Can there be an element which belongs to phi? No, because by definition it is the empty set, there cannot be any element. It means we are saying that if A is a subset of phi, then A is equal to phi. This statement it is true. This statement is true. Next is, if A, B, C are sets such that A belongs to B and B is a subset of C. So these are the conditions. So let us try to create some set. We are saying we have three sets. So first set we are considering, suppose it has an element A and we are given that A belongs to B. Now be very careful over here. We are talking about two things. One is A is a subset of B, and one we are saying A belongs to B. We are talking about the set B and it is given that A belongs to B. It means that we have A over here and some other element can be there. It means this set looks like it is the set A comma B. If in place of this it is given A is a subset of B, then we would have written element of A is present in B and some other element might be there. So compare these two. We have the set A is present over here, over the element of the set A is present over there. This is the term subset we are using. This is the term belongs to we are using. Now, and third thing that is given is B is a subset of C. So the set C will look like, B is a subset of C means every element of B is present in C. Every element of B this element is present over here, this element is present over here, some other element is there. Every element is present over here. Then A is a subset of C. Look at this condition over here. Then A is a subset of C we have to prove. To prove this thing, what we have to do, we will consider some x belongs to A. In this case, in place of x, we are saying A belongs to A. There is an element A in the set. If we are saying A is a subset of C, then for all A belongs to A or x belongs to A, we will have x belongs to C. What is happening over here? We are saying A belongs to A, but A does not belong to C. There is no element A over here. It is set A belongs to C. So we are saying that this statement is false, and these kind of examples, when we give to disprove a statement, these are called the counter examples. I am again explaining this thing. This statement is given. There were two cases. Either this statement is true or it is false. If this statement is true, we have to give the formal proof. To disprove this statement, to disprove means that we are saying that it does not hold for all A, B, C. We have given an example, we have shown with this example that there exist A, B and C. Three sets are there for which A is not a subset of C. So this single example is sufficient to prove that this statement does not hold for every element ABC. So these kind of examples we will see very frequently, and these are called the counter examples, and these are basically used to disprove some statement, not to prove some statement. If suppose we construct three sets over here for which this thing holds, there might be some set for which this condition holds. It doesn't mean that this statement is true for every element. But if we have constructed the example for which this statement does not hold, it means that it does not hold for every element. So this statement that is given to us over here, it is false. Next. If A, B, C are sets such that A is a subset of B and B belongs to C, then A belongs to C. Again, the set A we are considering, suppose it has an element A. The set B we are saying now A is a subset of B. When it is subset, we will consider it in this form, that element of A is present over here and B belongs to C. B belongs to C. This set B is present over here and element C is there. So we are going to write it has elements A, B, C. Now all the conditions are satisfied. A is subset of B, B belongs to C. Then does A belongs to C? No. There is no element set A present over here. So we are saying that A does not belong to C. So this will act as a counter example. We have given an example in which we have shown that there exists, what we have shown, that there exist sets A, B, C such that A does not belong to C. What we have shown, that this statement does not hold for all sets A, B, C. So this statement it is false. So this statement it is false. Next, A, B, C are sets such that A is not a subset of B and B is not a subset of C. Then A is not a subset of C. This statement is given to us. Again, suppose A is equal to, A is having one element A. We are talking about the set B. We are saying A is not a subset of B. It means A is not the element over here. We are writing the elements say B and C. And B is not a subset of C. B is not a subset of C. The element B is not present over here, it means B is not a subset of C. But what is happening over here? A is a subset of C. This element of A, it is present over here, it means A is a subset of C. So again, we have obtained the counter example to this thing. We are saying that it is not always true that A is not a subset of C. It may be subset of C, it may not be subset of C. So this statement does not hold for all ABC. So this statement is also false. Next is, if A, B are sets such that X belongs to A and A belongs to B. Some sets are given. It is given that X belongs to A. It means X is an element of the set A. A belongs to B. A belongs to B. This complete set is present over here. Then X belongs to B. Does X belongs to B? They are saying no. X does not belong to B. This is the example we have constructed. If A is this set containing X, B is containing this complete set X and element B, then there is no element X over here. It means that X does not belong to B. So again, this statement, it is false because it does not hold for all sets A and B. Next we have is some particular subsets of the real numbers. We are talking about the subsets of the real numbers, and they are also called the intervals. So when we were talking about the representation of real numbers using the set builder form or the roster form, we have shown over there, or we have seen over there, that it is not always possible to represent the real numbers using the set roster form. We cannot list all the elements. So let us look at how we can represent the real numbers. I am talking about, this is the real line we have. This is number 0. There are 2 points I am considering, A and B. I am talking about all the real numbers between A and B. I am talking about all the real numbers between these 2 points A and B. Suppose for example, I am saying this point it is -3, this point it is 5, and I want to write a set consisting of -3 is less than X is less than equal to 5. All the real numbers which are greater than -3 and less than equal to 5. So one way is using inequality. We can write set consists of X such that X is a real number and -3 is less than X is less than equal to 5. This is one way of writing this set. Another way of writing this set is using the interval notation. Interval notation is, this is strict inequality, this is with equal to sign. To distinguish these two, we are saying we use these kind of brackets. Brackets we will discuss in our next slide. Right now I am just telling you what is interval notation. We will write -3, this is less than equal to over here. We will write 5. Because this equal to is here, we are putting the bracket like this. We will see what is the meaning of these brackets in our next slide. This is another kind of representation. We are saying interval representation. This is just representing this set. We are talking about this set. We can write it in this form. Whenever it is written -3 with open bracket, 5 with close bracket, it should be clear to you that we are talking about all real numbers which satisfy -3 is less than X is less than equal to 5. Geometrically, what this thing means? How geometrically we can represent this? We are talking about, look over it. We are saying -3 is less than X. It means -3 is not included in this set. The number -3, it is not included. We use the dot like this. Number 5, it is included. If I will ask, what we will see over here, 3 does not belong to this set. If I am writing this is A, 3 does not belong to A, but 5 belongs to A. How we are distinguishing these two elements? We are saying when -3 does not belong to A, we are putting these kind of brackets. On number line we are using these kind of hollow dots. 5 is in this set, we are saying 5 belongs to A. We are using this kind of bracket. Number 5 is there and we are using the dark dot to represent this thing. All the number in between are there, so we will represent it with a dark area like this. So this is the representation of the subset of real line. This is, we have considered a subset of the real line. We can represent it in this form, we can represent it in interval form, or we can represent it geometrically. So we will discuss these three cases in detail now. So this is one case we have discussed. Next, infinite intervals. So when we are talking about the case x is greater than 2, this is 0, this is 2, it is greater than means this point it is not included, and we are talking about all the numbers greater than 2. How we are going to represent this? We use 2 is there, open bracket is there because 2 is not included. We will put a symbol like this. This symbol we are saying this is basically the symbol for infinity. This is symbol for infinity. We will, in our next slide, we will understand what is the meaning of infinity. We will see. So right now we are saying if the intervals they are infinite, we represent it in this form. These things we are going to discuss in detail now. Now first of all we are going to talk about the brackets. What are those brackets they are representing? Whenever we are using the square brackets and we are writing A, B, the terms we are writing in the square bracket, it means both the end points they are included in the interval. What this thing means? This means A belongs to the interval AB and B also belongs to the interval AB. We are talking about the condition A is less than equal to X is less than equal to B. We are talking about this condition. Whenever we are using the round brackets, we are talking about the condition A is less than X is less than B. What we mean to say, A does not belong to AB interval and B does not belong to interval AB. We are saying that we have the numbers between A and B, and A and B they are not the part of that particular interval or that particular subset. And always keep in mind when we are talking about the infinity, or further in next slides we will see we will talk about minus infinity, then we will always use the round brackets. We are always going to use the round brackets. So let's make these things more clear with some examples. Solve. 12 plus 1 whole 5 by 6x is less than equal to 5 plus 3x. So how we are going to solve this? It is 12 plus 11 by 6x is less than equal to 5 plus 3x. This implies us that 72 plus 11x is less than equal to 30 plus 18x. We'll get this value. And now if we will adjust the terms, what finally you will obtain? We are having 72 minus 30 is less than equal to 18x minus 11x, and this will imply us that 42 is less than equal to 7x. It means x is greater than equal to 42 by 7, that is equal to 6. We are talking about x is greater than equal to 6. So how we are going to write the solution set? First case we have when x belongs to n. We are saying these are the numbers 1, 2, 3, 4, 5, 6. We are talking about x is greater than equal to 6 and x is a natural number. It means 6 is the answer. 6 is included. 7 satisfies this. 8 satisfies this. So how we are going to write the answer? It is 6, 7, 8 and so on. We are writing the answer as 6, 7, 8 and so on. So all natural number after this they are included over here. Second case, when x belongs to R. Let us try to understand this case. We are having x is greater than equal to 6 and x belongs to R, real numbers. Plot the real number line. 0, -1, -2, 1, 2. Suppose 6 is over here. Now we are talking about all the real numbers greater than equal to 6. Greater than equal to means 6 is included and all the numbers after this. Now how we are going to write all the numbers after this? One way to represent this is, we can write the answer as x such that x is a real number and x is greater than equal to 6. In interval form, what we are saying, if we look at these numbers, there will be number 7, 8, 9 and so on. So there is no last number over here. There is no last number over here. There is no real number that we can say this is the last real number. So in place of talking about some real number, we just give a representation over here, infinity. So this infinity over here that we are writing, it is just a symbol. It is not a real number. It is just a symbol to represent that this thing that we are moving over here, this is unbounded. This thing represents that we are talking about something unbounded which keeps on going like this. Similarly, on this side we will use the symbol minus infinity to represent that this line continues like this, and we say on this right side it continues up to infinity, on left side it continues up to minus infinity. But note that these infinity and minus infinity, these are not the real numbers. So how we are going to represent this? Number 6 is included, we use the square bracket. It continues up to infinity. At infinity or minus infinity, we always use the round bracket. So in interval notation, this is the answer, 6, infinity. This is the answer in this case. Next, the things will be more clear to you with our next examples. Next, we are going to talk about 4 kind of intervals. The first is the closed interval. Closed interval means we are talking about two numbers a and b such that a is less than b. Closed interval, when we are saying it, means we are talking about the interval. This closed interval means both the brackets, they are closed. It is representing the set x such that x is a real number, a is less than equal to x is less than equal to b. If we represent this on the number line, we are saying, suppose we have a, we have b, both these endpoints are included and we are talking about all the number between these. This is a subset of R. Open interval, a comma b, both the endpoints, they are not included. We are talking about x such that x belongs to R, x is a real number, and a is less than x is less than b. This is the open interval we are talking about. On number line, we are saying we have this point a, this is the point b. Both the dots that we are using, they are hollow, they are representing that a does not belong to this set, b does not belong to this set, but all the elements in between them, they belong to this set. So these kind of intervals, these are called the open intervals. Next is semi-open or semi-closed intervals. So we have two semi-open or semi-closed intervals. One is right half open interval. Right half open means that it is open on the right. We are talking about closed on the left and open on the right side. We are talking about x such that x is a real number, a is less than equal to x is less than B. What this thing means? We are talking about all real numbers between A and B. A is included, dark dot is there. B is not included, hollow dot is there. So we are talking about the numbers greater than equal to A and less than B. Left half open interval, it is open on the left and closed on the right. We are saying it is X such that X belongs to R, real number, and A is less than X is less than equal to B. If we represent these, we are saying these are A, B. We are talking about all the numbers between A, B. A is not included and B is included. B is included and A is not included. So these are the four kind of intervals that we have. These two are called the semi-open or semi-closed intervals. First we have seen the closed interval, second is open interval, and these two are the semi-open and semi-closed intervals. Next is length of the interval. So in all these four cases, closed, open or semi-open or semi-closed intervals, the length is always B minus A. The length of the interval is always B minus A. So let us consider an example. This set is given. We have to write them in the interval form and determine their length. So 3 is not included, minus 3 is not included, round bracket is there, 5 is included, square bracket is there. Length of this interval, it is 5 minus minus 3. When we are calculating the length, either the bracket is open or it is closed, it will not change the length. Formula is same, it is B minus A. The length in this case we obtain, it is 8 units. Set B, we are saying both the inequalities, they are strict inequalities. Both the points are not included. We will write minus 5 comma minus 1. And length of this is minus 1 minus minus 5. Answer you will obtain, that is equal to 4 units. This interval, minus 2 is included. When minus 2 is included, we will have square bracket. 0 is not included, we will have round bracket. Length of this interval is 0 minus minus 2. The answer we obtain, it is equal to 2. Last is minus 1 is less than equal to X is less than equal to 4. Round bracket is there, minus 1, 4, round bracket, square bracket is there, because both the endpoints they are included. 1 belongs to this, minus 1 belongs to this interval, 4 belongs to this interval. This is the interval we are writing. So the length of this interval will be 4 minus minus 1, that is equal to 5 units. So this is how we write the intervals and how we write the length of the intervals. Now next we are going to talk about the infinite intervals. So when we are talking about the infinity, the first question that arises is infinity a number? So we are saying infinity is not a real number. It is not a number. It is just a concept, or this is the symbol that is representing that something is unbounded or limitless. It is just something to represent when we are saying 2 comma infinity. It means we are talking about the real numbers greater than 2, and when we are saying greater than 2, it means that something we are representing, it is limitless, that it is unbounded. This is just a symbol. This is not a real number. This is just how we can represent the intervals. So when we are talking about the natural numbers, we are writing 1, 2, 3, 4, 5, so on. We never write infinity over here because it is not a natural number. Whenever we are writing the set of natural numbers, we cannot write infinity over here. Infinity is not a natural number. Whenever we are writing the set of real numbers, and if I ask infinity belongs to R, so you will say no, infinity doesn't belong to R, because infinity is not a number. It is just a concept to show or to represent that something is infinite or some unboundedness is there. there is no specific numerical value or any real number assigned to infinity. More details about infinity we will come across when we will talk about the calculus. We will talk about the limits, we will talk about calculus, we will come to know about the infinity. So if at any place you come across anything like infinity minus infinity or infinity over infinity, we are not going to write that this is 0. We are not going to write that this is 1, because these are undefined operations. There is no definition of these operations within the limits of the real numbers. When we are talking about real numbers, we are talking about addition, we are talking about division, it is well defined. But when we are talking about the set of real numbers, these are not real numbers, so there is no definition of the terms like infinity minus infinity or infinity over infinity. So we are saying that these terms, these are the undefined terms. Wherever you will get the terms like this, you will say these are the undefined terms. So let us consider some intervals that are infinite. First we are talking about x is greater than or equal to a. We have some point over here a, and we are saying x is greater than and equal to a. We are talking about all the numbers greater than and equal to is there. We will write it like this. So we will write a. This interval, it is infinite, unbounded. How we will represent? It is going up to infinity. At infinity we will always use the round brackets. X is less than or equal to a. We are talking about the case point a is there. This is the real line. Less than equal to means this point is included. We are talking about all points less than equal to a. So less than equal to a means that a is now the upper limit we are saying for this interval. What is the lower limit over there? There is no lower limit, so how we are going to write? Minus infinity with the round bracket. So these are all subsets of R. These are all subsets of the set of real numbers. Next is x is greater than a. It is greater than sign, so it means a is not included, and we are talking about all the numbers greater than a. X is less than a. All the elements which are less than a, all the real numbers which are less than a. It means we are talking about, we start with minus infinity, we are moving from this side, we are starting with minus infinity, or we are saying we are considering all the real numbers on the left side of a. Last we have is x is a real number. When we are talking about, this is the point a we have. When we are saying x is greater than a is not included, we are talking about x is greater than a. We have infinity beyond the real numbers. This is just a symbol that we are representing that we can move limitlessly on this side. We can also move limitlessly on this side, all the numbers less than a. If we are saying x is a real number, it means that it can have any value from minus infinity to infinity. So this is the representation of the set of real numbers using the interval form. This is the set of real number using the interval form, and all these that we have studied over here in our previous slides, they were the subsets of the real numbers. So this was all about subsets. So you can try these problems at your home. So you can try these questions, and if you have any doubt regarding anything over here, then we can discuss them in your doubt session.